This lecture will cover extensions to the Cormack-Jolly-Sieber model that allows us to relax the assumption of equal survival of individuals. Topics include estimating survival for different age classes and modeling capture and survival according to individual covariates. From the last module, the CJS model assumes all individuals have the same capture or survival probabilities, and the fate of each individual and release cohort are independent. If these assumptions do not hold, we run the risk of underestimating precision, and it's plain to see these assumptions are not very biologically realistic. We know individual traits such as behavior and age can influence capture and survival. In addition, environmental covariates in certain years may influence growth of individuals in that release cohort. Extensions to the CJS models allow capture and survival of individuals to vary over the course of their lives. Cohort models allow capture and survival to vary by release cohorts, and individual covariates allow capture and survival to vary by individual characteristics or environmental factors. Organisms of different ages may be more or less susceptible to mortality. For example, young individuals with less experience or lower body condition may have higher rates of predation. In age-structured models, if individuals can be aged at first capture, then the ages and subsequent capture occasions are deterministic. Accordingly, the structure of age models depends on our ability to age individuals in the field. In many vertebrates, it is only possible to distinguish young or first-year animals from adults greater than 1 year. In some species, it is possible to distinguish between first-year, second-year, and adult animals. Individuals born in the same breeding season belong to the same birth cohort. However, we can only account for 2 of the 3 processes of age, cohort, and time in the same model. I'm not going to discuss cohort models in this lecture, but the readings develop this further. In 1981, Ken Pollock extended the CJS model for multiple birth cohorts to separate age and time. Let's consider an encounter history 0110 for a young individual released at occasion 2. In the probabilistic statement, phi is apparent survival for age v and occasion I, and p is capture probability for age v and occasion I. The superscripts y are young and a are adult. This translates as the young individual survived interval 2 and was recaptured at occasion 3, and now as an adult, the individual either did not survive interval 3 or survived the interval and was not recaptured at occasion 4. It is important to think about the interpretation of P3. By the time a young individual released at occasion 2 was recaptured at occasion 3, the individual is now an adult. This means the age model may not be appropriate for P because young transition to adults by the time they are recaptured a year later. If we are marking both young and adults, then adults released at occasion 2 are handled the same way, except adults that survived interval 2 and are recaptured at occasion 3 stay adults in the 2-age model. Here is the MIJ array showing the observed data for 2 age classes. The table shows age at release in column 1, release cohorts in column 2 that are defined as the number of marked individuals of age V released at occasion I. The recapture occasions start at occasion 2, and the M's are defined as the number of marked individuals of age V released in occasion I that were first recaptured in occasion J. The blue diagonals show the number of first-year individuals that survived the first interval and were recaptured, and the tan diagonals show the number of adults that survived the first interval and were then recaptured. Considering young individuals transition to adults after the first year, all other cells in tan describe outcomes for adults. Here is an example of the input data summary for the Swamp Squirrel Lab. Can you identify the data we will be using to estimate survival for subadult squirrels? Now let's take a look at the multinomial cell probabilities for two age classes. Phi and P are the CJS parameters for young and adult animals. R is the number of marked individuals for each release cohort. And the equations in the cells calculate the expected values for the multinomial likelihood. Here, if we multiply the number of young animals released on occasion 1 by survival over the first interval and the probability of recapture on the second interval, then we can calculate the expected number of adult animals observed on occasion 2. And in the next recapture occasion, the young animals transition to adults. The cell probabilities now include adults that were marked as young, survived the first interval and were not recaptured on occasion 2, and survived the second interval and were recaptured on occasion 3. Now we have modified CJS assumptions. We still have to assume individuals of the same age have equal capture and survival probabilities. The capture intervals must correspond to the time required to transition to the next age class. And finally, age must be correctly assigned to each new animal that is encountered and marked. Now let's explore setting up age models in MARC. This example is for individuals marked as both young and adults with 5 capture occasions. We have to use the parameter index matrices because age structure cannot be set up in the PIM chart. Notice the close connection between the triangular structure of the PIMs and the MIJ array that we went over earlier. Let's go over the PIM structure for a general model with age by time for Phi and age cohort by time for P. The first matrix is for survival of individuals released as subadults, and we code year-specific PIMs 1 through 5 for subadults on the diagonal. In the second matrix, we have survival of individuals released as adults, and we code year-specific PIMs 6 through 10 for adults down the columns. Going back to survival matrix 1, because young individuals transition to adults after 1 year, we code year-specific PIMs 7 through 10 to be equal to the PIMs for adults in the second matrix. The third matrix contains year-specific recapture PIMs for individuals released as subadults, and the fourth matrix specifies year-specific capture PIMs for individuals released as adults. Remember, we can't fit age structure on capture because the young are already adults on the first recapture occasion at time 2. Here is the PIM chart for the general model. Notice PIMs 7 through 10 are constrained to be equal for subadults and adults. Often the best strategy for building models in MARC is to set up the most general model in the PIMs and then fit reduced models in the design matrix. In this case, the additive model for age plus time for phi and just time for p. Note the additive model cannot be fit using the PIMS. Here, beta 2 is the effective age class on survival, and betas 3 through 6 are the additive effects of time. For capture probabilities, betas 8 through 11 are the effects of time, constrained to be equal for subadults and adults. Let's say there are body condition measurements associated with each individual in the input file. We can fit an additive model for age, time, and condition by adding a continuous weight covariate to the survival parameters in the design matrix. This model will fit parallel slopes of weight for each combination of age and time. So this is a fairly biologically realistic model that accounts for a fair bit of heterogeneity in the survival estimates.